Good morning, students. In the last class, we started the Q meter. Let me check whether it is recording or not again. Okay. So in the last class, we started with the Q meter. Good morning, students. In the last class, we started with the Q meter. So the Q meter main intention is to calculate the Q factor, and it is especially used in laboratory for testing the what is the radio frequency coils as well as the inductors as well as the capacitors. Okay. So in order to test them, we are using the Q meter, and we we can calculate the resistance of the those elements which are used for testing. Okay. So means whatever the element which we are testing those elements resistance we can calculate using a Q meter by calculating the Q factor indirectly. So here we have seen all the explanation in the last class, okay, but we left with some points because there was a technical issue while recording the what video, so that's why I didn't give the conclusion. So here we are having the what is it a phasor diagram. So when you are having the unknown element means let us suppose I use one element and that is a coil. I would like to test whether this particular coil is acting as a inductive nature or in the capacitive nature. We have seen the RLC circuit explanation and means in the initial stage of the in the what is it frequency that it is acting as a capacitive nature. After resonant frequency it is acting as a inductive nature, and at resonant frequency it is acting as a what is it the resistive in nature. The entire circuit is acting as a resistive in nature. We least bother about that one. We are only bother about using the phasor diagram. Okay, using the phasor diagram we can comment that whether a particular unknown element, it is especially helpful in our vector impedance meter, no? It is especially helpful in our vector impedance meter. Otherwise I'll do one thing, I'll skip off this explanation. I'll go to the there is a circuit explanation of the Q meter. The phasor diagram, I'll come to that one during the explanation of the vector impedance meter. So which we'll see in within a few minutes. Okay. So here we are having the this is what the circuit of the Q meter. This is what the circuit of the Q meter, and yeah, in this Q meter we are having the radio frequency oscillator whose frequency is adjustable one, and we have the shunt resistance which is very small, and this shunt across the shunt resistance we are trying to measure the voltage using the thermocouple voltmeter, and also the between the terminals T1 and T2 we are placing the components which are need to be tested, we are placing those components over here, between the T1 and T2 terminals, and the capacitor, we have a tuning capacitor to adjust this particular means to calibrate this particular circuit in order to get the appropriate result. We are having the tuning capacitor, and which is placed between the T3 and T4 terminals. Okay, so here we have the CD, and we'll just bother about this particular CD because we are not discussing about this diagram is especially used in what is it testing the on capacitor, inductor, and the radio frequency coils. Yeah, we have the coil, right? So whatever the coil which you would like to test, so that coil should be placed between the T1 and T2 terminals, and this is the circuit diagram for measuring this particular Q factor, and also for testing the radio frequency coils, inductors as well as the capacitors. Okay, so whatever the element you would like to test, that element should be placed between the T1 and T2 terminals. Okay, so we have the applications of the Q meters also. You just go to the textbook. If you are having any queries regarding the applications, let me know that one. In the exam, no need to explain the applications much. Okay. So the next concept is what is that vector impedance meter. So here in the vector impedance meter, we are interested to what is that calculate the impedance of unknown factor. We are interested to calculate the impedance of unknown factor means unknown, sorry, it's not the unknown factor, it's the unknown element. Okay, so we are interested to calculate the factor is different and the element is different, right? So we are interested to calculate the unknown element, oh sorry, unknown element impedance. So means I'm taking one thing like this. Okay, let us suppose I'm having one box. uh, this box maybe, or otherwise if you are getting confused, then I will take a particular element, means I may take a capacitor, or I'll take the capacitor. Okay, so by seeing the diagram, it is a capacitor. I'm sorry, the plates are not in parallel, but it is a capacitor. Okay, because we were drawing, it was not proper one. Okay, so it is a capacitor. So, but I would like to calculate. It is a capacitor by weaving the symbol. We can comment that it is a capacitor. But let us suppose we have one component directly. Means this component is directly given, and we don't know whether it is a capacitor or inductor. Inductor. But I would like to calculate the impedance of this particular element, as well as I would like to know whether this particular this particular element is a capacitor or inductor. This particular element is a capacitor or inductor. So to do that one, we are going with the vector impedance meter. So the vector impedance meter main intention is to calculate the impedance of an unknown element, the impedance of the unknown element, as well as in order to know whether that particular element is a capacitive in nature or what is it, inductive in nature, capacitive in nature or inductive in nature. So to calculate the phasor, what is it, impedance. So to calculate the impedance, what we are supposed to do means we are supposed to focus on the current and the voltage. Means I'm having the two options over here. I'm having the two options over here. What I'll do is I'll apply the constant voltage. I'll apply the constant voltage across the unknown element. So remember that it is a capacitor. By weaving this element, we can say that it is a capacitor. But for simplicity, what I'm doing is it is an unknown element, and between the terminals, means between the two terminals of this unknown element, I'm applying the voltage. I'm applying the voltage, and I'm calculating the current passing through this particular element. Okay, so I'm calculating the current passing through this particular element by taking the current I. So let us suppose this is the I, which is passing through the current, which is passing through the what is that, unknown element. By taking the voltage and the current ratio, by taking the voltage and current ratio, I'll come to know the I can easily calculate the impedance of this particular element. Okay, means one thing is I'm applying the known voltage and I'm calculating the current passing through this particular circuit. After that, I'm taking the current passing through this particular element. After that, I'm taking the ratio between these two. Then I can easily calculate what is the impedance of this particular element. And the other way of explanation is I'll apply the what is that known current, which is a constant current. I'll apply the constant current which is passing through this particular what is that element. So I'm applying the known current. Now I'm calculating the voltage drop across this particular unknown element. Okay, one is applying the voltage, calculating the current, taking the ratio. Other one is applying the current, calculating the voltage and taking the ratio. Then we can easily calculate the impedance of this particular element. And now we can easily calculate the impedance of this particular element, but the thing is we are interested to know whether this particular element is a what is it, a inductor or the capacitor. So for that you are supposed to extend your concentration on phase diagram, on the phasor diagram. So means I'll take the voltage waveform as well as I'll take the current waveform. I'll take the voltage waveform as well as the current waveform, and I'll try to compare these two phase what is that diagrams with respect to the phase. So by comparing these two elements waveforms, that is a there is a voltage waveform and the current waveform with respect to the phase, then I can easily comment that whether okay, what is that capacitive in nature or inductive in nature, capacitive in nature or inductive in nature. Okay, now so we can easily calculate that one. Wait a minute, it is overflowing. Maybe it may not be hold this one. Wait a minute, because our file should get stored proper way. We don't have the amount of voltage. Yeah, is it mean out of phase? Out of space. Better to remove some factors and take this from here. Because we have some there are some persons there who would like to focus at what time you are recording the classes. So bullshit. Hmm. Is it recording? It is recording. Hmm. Yeah, have the in your space. Okay, let's come back to this vector impedance meter. Yeah. So we are interested to calculate the means by calculating the voltage and current. mm, is one is applying the known voltage and calculating the current, or applying the known current and calculating the voltage. You can easily calculate the impedance, but the phase angle is the one which is decides whether the element is unknown element is a what is that capacitive in nature or the inductive in nature, capacitive in nature or the inductive in nature. Okay, component of range of frequency. Yeah. So this one, the vector impedance meter is especially means whatever the unknown element we are taking, and we are interested to calculate the impedance of that particular unknown element, as well as the type of the element, whether the impedance or whether the capacitive nature or the inductive nature. That means we can apply the signal over a frequencies, over a frequencies range 400 kilohertz to 110 megahertz. Okay, so this meter is especially used for measuring both the magnitudes and the phase angle of a component over a frequency ranges. Over the frequency ranges 400 kilohertz to 110 megahertz. So it is also used for knowing the type of the component, as I told you that. Okay. So the next one is the measuring magnitude. Okay, now how to measure the magnitude of a particular unknown element? It is determined by measuring the current through the unknown component when a known voltage is applied across it, or by measuring the voltage across the component when a known current is passed through it. Okay, passed through it. And another one is how we could measure the phase angle. Okay, so measurement of the phase angle, it is measured by determining the phase difference between the voltage across the component and the current through the component. That's what I told you, right? So we are interested to focus on the voltage waveform and current waveform, and we will calculate the phase difference between them, and we can easily calculate the phase angle. Means this meter is especially used for calculating the magnitude, that's the impedance, as well as the phase angle. But using the phase angle, we can comment whether the element is a capacitive in nature or the inductive in nature. In a capacitive in nature or the inductive in nature. So let us go over the block diagram. So here we are saying that this device is able to work over the frequency ranges from the 400 to 110 megahertz, right? So that could be done over here. That could be done over here. Okay, so here this is the front panel. Just like don't get confused with this diagram. It is like our CRO. It is not like our CRO actually, but you just get the what is that CRO picture in your mind, and there what we are doing, we are having the what is that the channel knobs, and we are adjusting the amplitudes, as well as we are adjusting the timing of the waveform. Okay, like that we are having the what is that a like that we are having one what is that vector impedance meter. So here also we are having the panels, and using the knobs we are able to adjust the means choose the a particular frequency range. We are able to choose a particular frequency range, and when we are choosing a particular frequency range means we are testing that particular component under a particular frequency range, under it means at a particular frequency, and we are calculating the impedance as well as the phase of that particular element. Okay, this is a front panel of our the front panel diagram of our what is that vector impedance meter. Okay, nothing to do with this particular diagram, but let us go with the what is that internal diagram of the vector impedance meter. Okay, so this one looks like what is that a bigger one, but very easy to realize this. Okay, so here as I told you that we have the let me go back. Here we are having the probes, and we have the panels. This front panel is having the what is that knobs to set or to select a particular frequency, and to choose a particular thing. Means we have the different options. We'll, as we move on, we come to know that only. So here we are having the range and the frequency selector. Okay, so we have the range and the frequency selector. These are used for how long we can test, and the frequency for selecting the frequency. Also we have this one. Okay, so here we are having the Wheels bridge oscillator. So wheel bridge oscillator, which is sitting inside our what is that vector impedance meter, for select what is it for generating the required frequency signal. For generating the required frequency signal, we are using the this particular oscillator, and after that we are having the accurate gain controller, and which is an amplifier with a feedback gain control. Okay, now so it is a accurate gain controller, no? and after that we are having the Z magnitude range switch assembly. So means in order to select a particular range of impedance, we are using the Z magnitude. So that could be we have the different what is it ranges of the impedances. We will see that one as we move on. So depending on the impedances which we are choosing from this particular range switch, we can say that the vector impedance meter is working in the constant current mode and the constant voltage mode. We will come to that point. Don't worry about it. And after that, we are having the AC differential amplifier to what is that measure the voltage drop across the unknown element, And, we have the two modes of operation. We'll come to that one. We have the AC differential amplifier and which is a trans resistance amplifier, or I can simply that it is a RT amplifier, which takes the responsibility to convert the current at the input terminal into the voltage form. Okay, the current to the voltage, which transfers the current into the voltage form um, by taking the multiplication between the what is it the input current and the resistance of this particular element. There is nothing but this one. So especially we are interested in the unknown component. Okay, don't worry about it. It is a trans resistance which translates the current into the voltage form simply. And after that we have the band pass filters. So amplifiers and the band pass filters over here and over here. So this channel is playing a major role in the voltage constant current source and the voltage constant voltage selection, and it is in the constant current selection. And we have the Smith triggers to convert our waveform into the what is it square wave, our waveform into the square wave. And because these are the sinusoidal waveforms, and we should convert them into the square wave format. We should convert them into the square wave format, and which is given as an input to the bistable multivibrator. And here we are having the what is it phase sensitive detector, which is a PSD. So the phase sensitive detector, we have the digital phase sensitive detector and the analog phase sensitive detector, but here we are using the digital phase detector to calculate the phase angle, phase angle between the what is that voltage and the current, to comment whether the unknown component is a what is it capacitor or the inductor. Okay, let us focus on the major part, which is a unknown impedance. Okay, so I'm having the unknown factor over here. I'm indicating that one as a ZX because it is an unknown. Whether it is a ZL or ZR, that purely depends on the calculation we can comment. Based on the calculations, we can comment. So here we are having the means we are placing the unknown component. We are connecting the unknown component at this particular point, and we have a voltage terminal to measure the voltage and the current terminal to calculate the current passing through it. Okay, and this unknown factor from the vector impedance meter, we are interested to calculate the magnitude. So this meter is acting as a magnitude meter, and this meter is acting as a phase meter. Okay, so based on the this magnitude is giving the impedance of that particular element, and the phase angle, phase difference gives the clarity whether the unknown component, whatever the unknown component we are placing over here, whether this particular unknown component is a capacitive in nature or the inductive in nature. Okay, so let us go for the what is it the process, how exactly the this particular vector impedance meter is trying to calculate the magnitude and the magnitude that's the impedance as well as the phase differences. Okay, so in order to go further, you just focus on this particular magnitude range switch. Okay, so let us go to the next slide. I'll come back to that particular diagram. Don't worry about it. So I told you that we should focus on the range switch, right? So whatever the range switch we are having, the based on that particular range switch, inside that range switch we are having the what is that selections now. So we have the impedance ranges from the 1 to 100, and another one is a 1K to 1M. Okay, so these are the impedance ranges switches. We are have the different impedances. Okay, so means the unknown factor, we don't know what is the impedance of the unknown factor, but in order to calculate the impedance of the unknown factor, we may focus on this particular set, that is a 1 10 times or the 100 times or kilo times 10 kilo times 100 kilo times or 1 mega. Okay, if you are choosing the impedance range switch to tune one of these particular component, then I can comment that the instrument is operating in a constant current mode. The instrument is operating in constant current mode. What it means, we are applying the known current. We are applying the known current which is passing through the unknown element, and we are calculating the voltage drop across the unknown element. So as I told you that we are having the unknown element. So this is the unknown element, and two ways are there to calculate the impedance of this particular unknown element. One is applying the current and calculating the voltage drop across the capacitor and taking the ratio between them, or applying the voltage across the unknown element and calculating the current passing through it. Okay, calculating the current passing through it. So in the constant current mode, we are applying the current and we are calculating the voltage drop across the unknown element, and we are taking the ratio between them. We can easily calculate get the impedance. So in the constant voltage mode, if you are choosing the impedance ranges which in one of these elements, then we will apply the explanation is reverse, means we will apply the known voltage and we will calculate the current passing through it using the current meter, that is the ammeter, and we will take the ratio between them, and finally we will calculate the impedance of this particular element. Okay, so constant current mode means the range switch, if the range switch is tuned to the 1 times, 10 times, or the 100 times, or if the range switch is tuned to the kilo, 10 kilo, 100 kilo, or 1 mega, then it's called as a constant mode. Means the instrument is working under the constant mode. Okay, let us come back to the diagram. Okay, so here over here, as I told you that the instrument can be operated in the two different modes. One is the constant current mode and the constant voltage mode. For the first point explanation, for the explanation point of view, initially I'll take the constant current mode. When you are taking the constant current mode, we are having the switches, right? So whatever the physical switches are there, switch positions are there. So these are the switch positions in the constant current mode. These are the switch positions, means the third switch is connected to this point, and I'm assuming this is the fourth switch is connected to this point, and the first switch is connected to at this point, and the second switch is connected to at this point. Okay, so these switch positions are indicating the these are the switch positions in during the constant current mode. Okay, now during the constant current mode means we are applying the known current which is passing through the unknown element. We are applying the known current which is passing through the unknown element. But when we are applying the known current which is passing through the unknown element, we are interested to calculate the voltage drop across the element, because we are supposed to calculate the magnitude, that is the impedance of that particular unknown component. So in order to calculate the voltage drop across this particular element, what I'm doing is I'm using the AC differential amplifier. This particular AC differential amplifier is the one which is calculating the voltage drop across this particular terminal, which is calculating the voltage drop across this particular this particular component, voltage drop across this particular component, because it is in the parallel connection. Okay, it is in the parallel connection. Now here we are applying the current. This current, yeah, and let us focus on the AC differential amplifier only. So this AC differential amplifier output is a means it is taking the voltage drop across this one. So this particular output will be what is it? This output will be the voltage, and this voltage is applied as an input to the what is that, magnitude meter. Okay, an active detector which is a magnitude meter in the sense, by using this particular AC differential amplifier we are calculating the unknown voltage, and we know the constant current. By using the current and the voltage, this impedance magnitude meter will display the impedance of that particular element. Okay, impedance of that particular element. Now let us come to the trans resistance amplifier, which is used for translating the current into the equal voltage format. So that is done with the help of this particular RT amplifier. So here we are having the input current. So this particular input current is converted into the voltage form, and it is passing through the band pass filter, and we are selecting a particular element. Okay, now using the band pass filter we are selecting a band of frequencies. Okay, so this particular voltage is passing through this particular terminal, and it is given as an input to the active detector. Again, one more active detector. So remember that the output of this element is given as an input to the Z magnitude. Output of this element is given as an input to the another one, which is a DC differential amplifier, DC differential amplifier. And this voltage, whatever the voltage we are getting from here, this voltage is compared with the DC reference voltage. If there is a change, means if there is a we are taking the differential amplifier. Differential amplifier means which will compare these two signals and gives the error signal. If there is a adjustment required, uh, means if there is a difference between the input signal what we measured and the reference signal, then there is a output voltage is generated. This output voltage is taking the responsibility to adjust this particular gain of means the frequency as well as the gain of this particular element. Gain of this particular element, when it is adjusted this gain, when it is adjusted the gain, then the magnitude range switch will means we are interested to um, switch the what is it impedances, whatever the ranges we have seen. So using this particular gain controller, using this particular voltage which is coming from the output of the DC amplifier, it is adjusting the gain of this particular element. When it is adjusting the gain of this particular element, this output is used for selecting changing the impedance range switch, changing the impedance range switch. Okay, so when it is changing the impedance range switch, again, the means we are interested to calculate the exact accurate value. We are interested to calculate the accurate value, as well as we are interested to calculate the type of the element, whether the inductive in nature or the capacitive in nature. Okay, so that is what the intention of this particular what is it, a vector impedance meter. Okay, so this based on this value it is adjusting the gain, and because of that the impedance range which is shifted. So like that, we are able to calculate the magnitude of the impedance, means we are able to calculate the impedance magnitude by using this particular output, But we are interested to know whether the unknown element is a capacitive in nature or the inductive in nature, So for that, what you are supposed to do means you are supposed to take the phasor diagram. So I'm just drawing the phasor diagram which we have seen in the last video. Better I'll go back to this one. Same explanation you can consider, but no need to draw this diagram in the exam. Okay. So here, if you see this one, we are having the this is a phasor diagram. Um, you may take this is a phasor diagram, right? So based on this phasor diagram, we can comment that whether the unknown factor is a unknown element is the impedance, or sorry, inductor or the capacitor. We can easily calculate that one by concentrating on the phasor diagram. So this is a phasor diagram. It is a current passing through the element. It is a constant current. Whatever the current you are applying, I'm assuming it is a constant current passing through the unknown element, and it is a voltage drop measured between the uh, measured across the unknown component. If this particular diagram means, if the when you are placing the voltage and the current phasor on the phasor diagram, if the current is leading factor and the voltage across the unknown element is a lagging factor. Better I'll come back to the diagram itself, because it is already drawn as a ECEL, right? Okay, wait a minute. So here what I'll do is I'll take that. Okay. So here we are interested to know whether the element is of inductive in nature or the capacitive in nature, right? So I'm just taking that diagram. Okay. So here we are applying the constant current now. This is a constant current which is passing through the unknown element, and if after we know the what is that constant current which is passing through the unknown element, and we calculated the voltage drop across the unknown element using the AC differential amplifier. Now if at all that voltage is placed over here to the below of the phasor diagram, below of the phasor diagram, okay, to the below of the phasor diagram, I'm assuming that this voltage is a V. If you take this particular diagram, in this phasor diagram, I is the leading factor, and the what is that voltage is a lagging factor. So means I leads the voltage V, current leads the voltage. So if we are having this kind of response from the what is that from the what we say, from the unknown element, means when you are applying the constant current and trying to calculate the voltage drop across this one, and if you are putting those two values on the phasor diagram and current is in this position, at this position, and the voltage is at this position, then I can say that the current is leading factor and voltage is lagging factor. Current is leading factor and voltage is lagging factor. Or I can comment that current is leading the voltage or voltage is lagging the current. By how much angle? You can take the different angle also, but it is a 90 degrees, which is a 90 degrees. Lagging means I can say that current is leading the current is leading the voltage by 90 degrees. Then I can current is leading the voltage by 90 degrees. Then I can comment that the unknown component is a capacitor. Then I can comment that the unknown component is a capacitor. Okay, now if the whatever the voltage, so as it is a capacitor now, I'm indicating this one as a VC. So if whatever the voltage you are calculating across the unknown voltage, if that particular voltage is when you are taking that voltage value and placing that one on the phasor diagram, if that particular voltage is means that value is existing above this line, okay, now above this line, then this one is called as a inductor. Okay, now so it is called as an inductor because voltage is leading the, in this case voltage is leading the current. Voltage is leading the current. Okay, now if the voltage is leading the current, then that kind of response is called as a inductive in nature. If the current is leading the voltage, if the current is leading the voltage, then that kind of response is called as a capacitive in nature. Or simply I can say that if we are putting the what is that current and the voltage on the phasor diagram, if the relation between the current and the voltage looks like this, okay, looks like this, so this is the voltage and this is the current, then I can say that it is an inductor. The unknown element is an inductor. Means I can say that it is a positive 90 degrees. Actually, it is a negative 90 degrees and it is a positive 90 degrees. Then the voltage is leading, current is lagging. Okay, so then it is a inductor. If the response is like this, if we are putting the voltage and current values on the phasor diagram, the response is like this. Means a voltage is lagging the current or current is leading the voltage. Then I can comment that it is a capacitor. The unknown factor is a capacitor. Okay, so this is a phasor diagram. Means by using the phasor diagram, we can easily comment that whether the unknown element is a, what is that, capacitor or the inductor. Capacitor or the inductor. Okay, now. So as I told you that this one, RT value. So here we calculated the magnitude of the impedance, and we adjusted the range switch also based on the this factor. And here we are interested to calculate the phase difference, right? Phase angle between the voltage and the current. Phase angle between the voltage and current. So these two waveforms takes a responsibility, means these two Smith triggers takes a responsibility to convert your what is that, sine wave into the square wave, sine wave into the square wave from the waveform coming from this particular element as well as waveform coming from this particular element. And there are two square waves, and I'm using the what is it, the digital phase sensitive detector. I have taken the digital phase sensitive detector, right? Digital phase, we are having the two types of phase detectors to calculate the phase difference. One is a analog phase detector and a digital phase detector. We are interested to use the digital phase detector over here. So these two are generating the square wave, and we are trying to calculate the phase difference between them using the differential amplifier and the indicator. So differential amplifier followed by the integrating capacitor. So based on these components, we can easily calculate the phase difference between the two signals. Phase difference between the two signals. If the phase difference between the two signals is positive in nature, then I can say that it is a inductor. If the phase difference between the two signals is a negative in nature, then we can comment it as a capacitive in nature. Okay, the unknown factor is a capacitor. The unknown factor is a capacitor. Okay, so this is all about in constant current mode. If the element is acting, working under the constant, if the component is working under the constant voltage mode, constant voltage mode, at that time the switch position will be changed. All the switch positions will change from the actual position to this one. Okay, so all the switch positions will change. All the switch positions will change. Now, in the constant voltage mode, what we'll do is we'll apply the known voltage. We are applying the constant voltage, and we are calculating the current passing through this particular element. Current passing through this particular element, and that information is given as an input to the what is that, magnitude. Okay, now so that is the impedance magnitude meter. So which will take the ratio between the applied constant voltage and the current passing through this particular element, and it will show the impedance of that particular element. And here the operations are reversed. Okay, now so the DC operation amplifier is output of this one is used for what is it, controlling this particular element, and again the same explanation. The switch trigger is the one which translates our sinusoidal waveform into the square waveform, and measure the difference, phase difference between them, and display the information whether it is a capacitive in nature or the inductive in nature. Okay. So as I told you that this channel is playing a major role in the constant voltage, and this channel is playing a major role in the constant current mode, right? So the thing is, whatever the constant current mode explanation we have seen, same thing, but only the thing is the switch positions will change in the constant voltage mode. You can explain either of the one. You can explain either of the one mode of operation. Okay, now, so this is all about your vector impedance meter, right? So let us see that time. Okay, vector impedance meter. Okay, we'll stop the explanation because it is done with the vector impedance meter. Okay, we'll stop the explanation over here.